So that is the positive here, it's like so this T plus T that I have there, I get the following with this, mu minus 1 over 2, and 4, gamma minus 1 over 2, and 4. And now I go this I solution that would be x, the x that I wrote there, but now I will get it in this way. And what happens is that I get the same kind of matrix, minus 1 over 2, and 4, this matrix block, mu minus 1 over 2, and 4. And now I have this another system. So in the same way, this is the same kind of operator as before, so I will go Dirac operator in the sense that it's not the real Dirac one, but in the sense that when I make the product, I get the Laplacian in that way. Right? So now, I have to scale it this way, I get here another matrix that was u, but it's only the first part of the derivative, the coefficient. And now the good thing about this, that it's to be kind of maximum, but it's not hard for the conductivity equation. So what happens is that now, when I do this kind of thing, P minus W C of theta, this is actually the equation that I wanted to have, minus k squared, I A plus q. Okay? Yeah, that's q. And the same kind of thing happens if I do this reverse, and if I use like a conjugation. So it's like I have been able to get from zero different equations. Can happen also with the conductivity equation. Actually, the same kind of thing. Alright, and now the good thing is that the equation that we have is a zero different equation, but contains two derivatives of the coefficient. Because you see that when this hits this already has first part derivative, when this hits, you will get like second part derivative. So now we are somehow in the close to this scalar equation. Alright, now the procedure is the following. Now this is theta, and this is equal to 0. So this is the kind of equation. So now, let's think how we recover the solution. So the way that we recover solution for Maxwell equation is we subtract solution for this kind of chemical equation, vector chemical equation, then I get E, gamifying E as V minus W E of theta, and then I get the X, just making this a scale, so this is X, I'm making this a scale, and now if the E and H, the little one, the standard part, are 0, then I get solutions for Maxwell equation. Right? So that actually will be our procedure to do this thing. Using the techniques developed by Habermas at that time. So now, as I said before, for the beginning I tried to complete what was the idea. It was just trying to construct like, at the same time that the electric field were kind of dense and the magnetic field was not dense, or they could be negligible, and the other way around to get this information about the coefficient. I said that could happen for the first integral entity, but I said that was difficult. Now, we have this kind of procedure to deal with the Maxwell equation. We are going to use the same kind of computation here to prove the following new integral formula. So this is mu1 is equal to integral formula. So the one I got before now, if we have the C mu1 gamma 1 is equal to C is mu2 gamma 2, we can prove this integral formula. It's just that the Q1 is minus Q2. So when Q1 and Q2 are the potentials for the corresponding solutions, satisfy the following, this is C1 equals to mu2 equals to 0. Okay, now this is solution for Dirac. So Dirac equation, so it's a solution for a system of this type. So it's just, if you want to construct it, you have to construct it first, and then use this. And you don't have to do anything about the scalar component because it doesn't have to be like producing any Maxwell solution. But now this one is again solution for this kind of equation, but has to produce Maxwell solution. So it has to have scalar components equal to 0. Has to produce solutions for Maxwell equation. Alright? Has to produce solution for Maxwell equation. Right. Okay, now I will go into how to construct the solution, because most of the people constructing this solution for this is following the same idea as Habermas and Dirac, but there are some technicalities because you have to make this match, and also because you have to get different orders in the electric part and in the magnetic part. So it's a bit more technical, but I won't go into details to this thing. But now what happens is that after we get the corresponding trivial solution, the same kind of solution that you have over there, and using the same kind of properties that we have from the paper that Habermas and Dirac, like specified situation, we can prove that Q1 is equal to Q2. Alright? The Q1 is equal to Q2. But that's not the end of the problem, because the Q1 is equal to Q2, it means that some relations that involve second partial derivatives satisfy that they are equal. Alright. So now what can we extract from Q1 was equal to Q2? The reason why I asked to write this, to use the projector for this, is because the kind of system that we can deduce from the quantity Q1 and Q2 is a bit ugly because it's too long. But I won't write it. I will just say what is the idea. What is the idea we have? So the thing is that what we are able to prove is somehow from Q1 and Q2 we can deduce that the difference of gamma 1 and gamma 2 satisfies the following condition. 1 over 2 minus gamma 1 over 2 plus B gamma 2 1 over 2 minus gamma 1 over 2 plus A gamma 1 over 2 minus gamma, I'm sorry, this is 2, 1, and every time is 1 over 2 plus B mu 2 1 over 2 minus mu 1 1 over 2 equal to 0. That's the first equation that we have. This is A, and now the second equation that we have is mu 2 1 over 2 minus mu 1 1 over 2 plus W, capital W. W mu 2 1 over 2 minus mu 1 1 over 2 plus C mu 2 1 over 2 minus mu 1 1 over 2. plus G gamma 2 1 over 2 minus gamma 1 1 over 2 equal to 0. If you think it is just like a zero perturbation system for solutions that are of this kind. Right? So now the point is that we know that the difference of these two solutions, of this solution, I mean this concept, the difference of this conductive coefficient and the difference of this coefficient are H1 in the whole arc, because we are sending it in such a way that they were equal outside. And actually the point is that those are company supported. So what points out here is that for this configuration, the solutions are like zero, right? And they are equal, the solutions are zero, and therefore the coefficients are equal. Now the point is that happens if every coefficient would have like good properties. But the point is that the only thing we know is that A, G, you cannot say from here because I have the same with A, B, C, and D. So the limit is A, B, C, and D are L infinity one. So for those are okay. But not for those. This V and W contain second quadrant derivative of the same coefficient. So they cannot be thought of as quantum infinity. They are like more singular. So the idea is that in order to deal with this system to prove the unique continuation for this, we didn't go to the for this kind of result. What we did was actually use the same kind of estimate that Rho, Haberman, and Tataro to get the result of unique continuation. And yeah, that's okay. So that's why I'm going to tell you how to do this. This is very simple. Yeah. Okay. That is very simple. Yeah. So the point is that if we have that S and G belong to H1 of R3, and they are company supported, that H is equal to G equal to 0 is equivalent to F plus GX plus AX plus DJ is equal to 0 and plus G plus W, G plus CG plus DS. And this kind of potential are this kind of singular potential, this G and W. So this is the unique principle here, and the idea to how we did it, probably there are many other ways, but since we have already this estimate for Haberman at the time, was very straightforward to use them. So what we did is just, if they are company supporting, F and G are company supporting, this U, F and V is XG, they belong also to H1 of R3. And the reason is because if they are company supporting, the exponential rho that I can produce this solution, they disappear immediately. Alright, so now this U and V, instead of satisfying this equation, they satisfy the following equation. They satisfy U, and they make the bracket the same, right? And the same for this. That's 2 that's plus grad, V, that's the same thing. So what I mean is that the only thing is changed is the derivative is the exponential at this kind of operator bracket. So it's the same coefficient. U and V satisfy the same equation, but replacing the Laplacian for this funded operator. They are called funded operator. Okay. Alright. So now in order to prove that U and V are equal to 0, I'm going to introduce what is the symbol for this. So the symbol of this operator is P theta of psi. It's the modulus square of psi minus 2 psi secant of psi. Right? Okay, and it's very simple to check the following property. That P theta, and now I put here, this is the modulus, this is complex, so this is the modulus, and I put it to a power of h of the Fourier transform of U in R2 is the same as having P theta h minus 1 of the operator 2 theta grad U Fourier transform in R2. Right? Because this is actually one full power of. Okay. Oh, sorry, I have a problem. And this is always I have the same problem. U is this, and V is this. So V has this thing, U doesn't have it. No, this V is supposed to be capital V. And this is supposed to be W capital W. Yeah, sorry for that. Yeah. Alright. Yeah. So then we have this kind of property that is immediate, right? Like we can lower one power of pieces because we are putting the operator. So this, so now that you're very used to that, people in the community and everybody is not that used to that, but this is some kind of type of space, right? It's not fancy, but it's very similar to some kind of type of space. So with this kind of homogeneous, so it is drop there and to the power of x. Right, so then this property that you have there is nothing but to say that U in x dot s of theta is equal to Laplacian plus 2 theta grad U, and now x dot in x minus 1 of theta. Right? So this Haberman and Tataro introduced a space for constructing this TO solution, and they use it not only for the construction of the solution, but for getting some improved TK that it was missing, totally missing from the techniques that we had available before that. So they improved this TO solution for C1 and the remainder, and that's the property of the remainder was exactly missing for the C1 connectivity. So now the point is that one can use those spaces to just to prove the unique continuation, and the thing is very simple. The thing is just that by perturbation, if you see that the system that we have here is just this kind of operator plus perturbation. So what we can do is just return here and understand the potential that we have here, and if we can bound the potential by the left side with a small norm, we are fine. Because that means that the U and V are 0 and the F and G are 0. And I want to do that here, but actually that's the case. That's the point. That's what they prove for different geometry. It's the same kind of spirit is what they prove. So they managed to prove that for some S that I would say already is S equal to 1 over 2. For some S, they are able to prove that these potentials apply to this operator with this norm is less or equal on the right-hand side, and what you get is this, that x dot s zeta plus v x dot s zeta is less or equal to a little constant that you can make as small as you want, times the same quantity, u in x s zeta plus v in x s zeta. So from there, since this is a constant, you can do it as small as you want. As zeta goes to infinity, you can prove that u and v are actually equal to 0, and f and g are equal to 0. Okay? And then you have the property of unique continuation. Alright. Yeah, then you have the property of unique continuation. Alright. And just to mention how that happens, because we are so used to that here in this community, so I will tell how that happens. So the h is actually 1/2, and that's related to the regularity of the potential. Right? So the this h 1/2 is related to the regularity that you have there. And the idea behind these estimates that are there, they are just localization type estimates. So they are just localization type estimates that were introduced in this concept of Harman and Tataru, and the kind of estimate what they follow were that slash d of z, so numbers 1 and 2. X now is a cut-off function or cut-off function on the spark class. It can be bounded in L2 just by d of z, so 1/2, u in L2, that this was just like u in x dot 1/2 of zeta, and just because it is homogeneous and this is not, it's just like the non-homogeneous space. So this is x, u, and this is x 1/2 zeta. So this is kind of estimate, and the reason behind this kind of estimate is like here, this is either a cut-off function or a function in the spark class. So what we are doing is multiplying by u in the Fourier transform we are composing, and when you compose, you are somehow dispersing the mass of u. So the mass of, the Fourier transform of u. So the mass of the Fourier transform of u cannot get concentrated, for example, here, and where this function that is, it will be the problem. So this kind of thing cannot happen because of the convolution. And actually the point is that you can do that at the same order as the modulus of zeta. And the reason why here we have the modulus of zeta, or the place that you can put in this way is the modulus of zeta, the reason is because this, the modulus of d of z, it's the characteristic surface, or is the symbol of this second part differential operator. It can be decomposed in two parts. One part which doesn't vanish, and another part, also more than one, another one which vanishes, of more than one in the characteristic surface of this. The part which doesn't vanish is actually of the other zeta. And the part which vanishes actually, it can be controlled because of the convolution. So that's the reason. Alright. And yeah, I mean, look at that in general, you cannot have this, you don't have the cut-off function here. So if you don't have like that this is somehow localized. This effect can be seen as well in Kahneman estimates, where you are doing somehow like controlling the L2 norm, for example, in bounded domains, the L2 norm will power down by the operator, adjusting in different scale. Okay, so yeah, so that's what I wanted to tell you. And I wanted to point it out that the chain estimate can be proved to use unique continuation. It has to emphasize there is a big relation between unique continuation and this kind of problem, or this kind of inverse boundary value problem. So right, to sum up, I would like to tell you that what we have been able to prove is just an inverse boundary value problem, unique for an inverse boundary value problem for mathematical equations, which is one to that it matches the non-result for the Calderon problem. We have used that the standard technique of CGO by using the method developed by Harman and Tataru. In order to construct this solution, what we did was like constructing a zero order perturbation whose solution were related to the mathematical equation, so there were these kind of relations. And we applied the same kind of technique that Harman and Tataru. And just in case that, because here there are more technicalities and the ideas can get hidden, the idea why this problem becomes difficult, as far as I know, is because the way we have to construct the solutions, I mean, the whole problem lays in constructing good family of solutions. The point is that the way we can construct the solutions are now by perturbative methods. So we are making perturbations of, in this case, actually, zeta-plane. And the point is, the less regularity you have with your coefficients, the higher is the perturbation or the more singular is the perturbation. So it's more difficult to control how the solution should behave. And that's basically the difficulty right now in this kind of problem. So yeah, I think that's all I wanted to do. Thanks. If there is I have a question, can I ask you one question? Yeah, it's like, what came before? The introduction of the spaces or the average? So it's like, if you cannot do any average, if there is like a data recent paper using this L2 delta zeta, I have a read, and they claim that they have got this idea of the averaging using these various spaces. I don't remember those, I can tell you later. But so then it's like, what came before the averaging? And then you introduce the spaces. Yeah. Okay, thank you. Well, first of all, I want to thank Herbert and Christoph for the kind invitation, but I also really want to thank the two of you for all the effort that you put into making this very lovely program. I know it's a huge effort, and I'm sure you think of much more pleasurable things to be doing, but we're all benefiting from this. I mean, I found it there's a lot of photos on the wall, so thank you very much for your effort to appreciate it, especially for the young people. I think it's been very good. So, anyway, so let me Again, I was asked very recently a question from Roberto Ruiz and Antonio Bartolo. They were interested in a question about the classical party limit maximal function and how it behaves when you take averages of it along lines. Okay, so this is a question that came about from their work. They've been doing for many years on the Helmholtz equation, and in particular weighted inequalities for the Helmholtz equation, and it's related to weighted Sobolev inequalities, and all of this comes dates back to a very famous paper of Hennig, Ruiz, and Sog on uniform Sobolev inequalities. This paper seems to is living a second life now. I've been to a number of conferences in the last few weeks, and there's been many talks on variants of this paper of Hennig, Ruiz, and Sog. So the questions what Alberto and Tony were interested in, they were interested in a certain class of weights. So these are weights that satisfy the so-called the radial Lisu-Hansa-Takeuchi condition. So this is a weight that satisfies the condition. What you do is you look at the radial conjoint of this weight, and then you use the X-ray transform, and you require that to be bounded. So you can express this nicely in terms of some norm of the weight to be finite, and now these days, again, this norm goes by the name of the triple norm. So what Alberto and Juan Antonio want to know is does the classical party limit maximal function behave well with respect to this triple norm? Is it bounded? Okay. So they had some reasons to believe that it was the case. They knew of several consequences that were true, and then the other consequences that they would like to be true. But it turns out to be not the case. Okay, so it's unbounded. The computation is not particularly difficult, but you have to do a little bit more than test the inequality on the characteristic function of a small ball. You have to take a sum of characteristic functions of small balls that are strategically placed. So this is a well, it's a triple, I won't write down, but it's a triple norm inequality, just asking with respect to this norm that is the hard-load maximal function bounded on this norm. So this is but anyway, that was just a trick. It just started to make, it just reminded me of another family of problems, which is what I want to talk about. And these are, they have the same sort of flavor, but instead of taking a classical maximal function and looking at averages over straight lines, you build a maximal function by taking a function and looking at averages over straight lines. And so there's kind of a large variety of problems that can be tapped in this way. We've already heard a very beautiful talk from Malavika. She was talking about a certain aspect of this. But there are other problems that I thought it might be a good time to revisit these problems. There are a lot of what I still think are quite interesting open problems, unsolved problems. And so I just want to use this hour to tell you, look at a few of these questions, tell you a little bit about what we know, and tell you what we don't know. Okay, so I'm going to begin by looking at these maximal functions. So this is going to be defined with respect to a line configuration. So I'm going to take a bunch of lines. Oops. Okay, so these are in some Euclidean space. So for me, these are lines mean finite line segments, but they can be quite general. They can have any position, different lengths, different directions. They could be finitely many of them. There could be infinitely many of them, uncountably infinite. But no matter what the configuration of lines, you can associate a maximal function the following way. I take a line segment here, and I'm going to consider a probability measure, sigma sub L. So this is just the normalized arc-length measure of that line segment. I'm just taking one-dimensional Hausdorff measure, restricted to that line segment L, and normalized with mass 1. So with respect to this probability measure, I can consider an averaging operator of a function simply by convolving with it. So this is averaging the function f over this line L at a point x, and then I just take the supremum over all my lines in this line configuration. That gives me a maximal function I'll call m sub L. And the basic object is to try to understand the LP mapping properties of this maximal function for a given line configuration. Okay, so as you can see, there's lots of different types of maximal functions that arise this way. Yes. All the line segments in your configuration. So you fix a bunch of lines, finite line segments, and then you take the supremum over all the lines in that line configuration. Or infinite or uncountably, infinite, for instance, Monavica talked about an uncountable collection of lines. Let's begin in this way. So this is you can sort of see many examples, the detailed problems are looking behind the scenes, so that's just section. There's many line configurations where you can know LPS fits for 18. Okay. But there are some, Monavica was explaining to us, there are some interesting line configurations where you do get LPS fits, and you get LPS fits for all t because of 1. Okay. But let me begin with the general result. So this is the result of my CRIS. So it's an old result. Okay, this goes back, I don't know, late 80s, early 90s. And what Mike's result says is that, okay, you might have some nice interesting configurations of lines where you get LP boundness for all t bigger than 1, but you never get these type 1-1. That always fails. Okay, so more precisely, what his result says, suppose you start with a finite collection of lines, let's say n of them, with distinct directions. So that's the key word. Okay, they're all pointing, you have n lines pointing different directions. I don't care how small the angle separation is between these lines. Then you get a bound on the weak type 1-1 operator over the corresponding maximal function. Okay, and it blows up with n. Okay, that proves that this is bounded from below by some absolute constant, only depending on the dimension that you're in, times n. So it's the advantage you get. Okay, so Mike gave a very nice, clever algorithm that no matter what the line configuration is, the algorithm tells you where to place strategic